Hi Bobcats! In this video we're going to take a closer look at ionic bonding. So ionic bonding happens when a metal bonds with a nonmetal, and the metal ends up with a positive charge, the nonmetal ends up with a negative charge, and the two ions are held together by the attraction of opposite charges. We also can throw into this mix polyatomic ions, which are things like the hydroxide ion, where you have a group of atoms that collectively have gained or lost an electron to end up with a charge, and altogether, though that cluster acts as a single species. From physics, we get Coulomb's law that tells us that the force of attraction between particles with that are charged is given by this equation. K is a constant. Q stands for the charges themselves. So Q1 and Q2 are two charged particles. So there we go. Those are our charges. And then R is the distance between those charges. Distance between charges. And if we look at the mathematical form of this, putting the charges up in the numerator means that the bigger the number we have for the size of the charges, the bigger the force will be. Having the distance between the charges in the denominator means that the distance gets big, the force between them gets small. So if we want to have a big force of attraction, we need to get the particles very close to one another. I'd like to try to model how ionic bonding works with a very simple two-dimensional model here. Imagine that we just have a positively charged ion here. It is attracting uniformly in all directions any sort of an ion that has an opposite charge. So let's say a negative ion comes along, and well, it's blocking this positive charge over on the right-hand side, but not on the top. And so another negative ion might come along and be attracted to it up above. Another negative ion might come and be attracted to it down below, and another one over here on the side. Now those negative ions are pretty well blocking out the positive ion, but if there's a positive ion floating around in the upper right, it is going to see the attraction to two of these negative ions, and it might fill in this spot, or another positive ion might fill in down here because there still is attraction. If somebody comes in from the lower left corner, it's going to see two negative charges, so that might attract a positive, and ditto, if a positive charge comes in from the upper left, it's going to see two negatives, so that may have it come in. And so this process just keeps repeating, where these oppositely charged ions keep filling up space until pretty much you run out of ions. The ionic compounds tend to build up these crystal lattices that extend to tremendous numbers of positive and negative ions. The image on this slide is trying to show you a glimpse into a more three-dimensional representation of one of these crystal lattices, because real ions have all three dimensions to work in. And if you focus on any one ion, so for instance, what if we focused on this negative ion right here? Its nearest neighbors in all directions are going to have the opposite charge. So if we go towards the back, there's a positive charge. If we go to the left, there's a positive charge. If we go to the right, there's another one. If we move to the front, there's a positive charge. If we move to the top, there's a positive charge up there. And if we move to the bottom, there's a positive charge down there. So in all directions, each ion is surrounded by ions that have an opposite charge. When we talk about the particle nature of matter, for most elements, we tend to talk about the particles in terms of atoms, and that's what's being illustrated over here in part A. This might be something like the element helium. There are a few elements that consist of diatomic molecules. Those are what I call the Brinkelhoffs, so that might be something like bromine or iodine or oxygen that will exist here, like what's being shown in part B with those diatomic molecules. And molecules can be much more complicated than that, but with molecules, you tend to have these closed units. You tend to have these closed units that we call molecules that are complete. And once all of those atoms have been added to the molecule, there's no attraction of additional atoms to it. But with ionic compounds, we end up building these tremendous extended three-dimensional crystal structures. And the purple that's indicated over here in this drawing is supposed to be showing you a formula unit. This is supposed to be a model of sodium chloride, and when we go to write the formula for sodium chloride, we don't write in a I'm going to guess there's like 42 sodiums in there, and then Cl42. That's not what we write. We're going to write the empirical formula, the smallest whole number ratio. So we're just going to write NaCl when we go to write the formula for an ionic compound. And so that formula unit is what is shown with that purple outline. And that's the formula unit is simply all of the ions that are shown when you write the correct formula for an ionic compound. We took a brief look at ionic bonding in terms of the attraction of opposite charges by Coulomb's law. For that attraction to be big, the particles have to be close to one another. And then the bigger the size of the charge, the bigger the force holding those ions together. Also with ionic bonding, we ended up with extended three-dimensional crystal structures. And so when we go to talk about a particular compound, we talk about its formula unit, which is its empirical formula, that smallest whole number ratio between the cation and the anion.